has to be expressed in a certain doctrine. You see, you have doctrines of theories, doctrines of stuff. So once again, not that they're sort of all arbitrary structures any more than they're arbitrary ringing. There are different doctrines. So descent is one doctrine. Algebraic theories is another one. And you can find several ones. But then once you have that, it's an obvious question. But for a given functor, I might try to apply some different doctrines. Do I get the same result, the same descent problem? So there comes the theorem. Yes, you do. I mean, under the side assumptions. So Beck gave a talk on that in '67. And, I'm sorry, I'm talking about it. Lately there's been a big debate. So Beck didn't do it, I did it first. How can you possibly do it? Well, we had discussed it over the years before, or 2 years before. This is not a long time ago. And so there's sort of dissent in this general philosophical sense, and then dissent in the typical sense of dissent data, but also algebraic structure and several others. Once you think of it, it's kind of a way, even non-categorically, that you could have a construction which is take any function and take its derivative. And if you're given the derivative, you don't know what it came from. But if you add a bit of data, namely the initial condition, along with the derivative, then you can integrate. You see, so the map that you're trying to invert, you adjust it in two ways. You first have the actual structure, and then you have the adjoint, and you can lift it in comparison. Is that all right?
Two words. Very shortly. I would like to make a remark which is related to what Pina said just a few minutes ago. That's part of the first influence that Bill had on my research, unfortunately many years ago. That's the idea of functorial semantics. The idea that models are functions, which has a presupposition that the domain of the model as theory is a category, because otherwise the function cannot be defined. So this calls for a categorical descriptions of theory, of a theory. And part of this is the description of logic as in categorical terms. So the notion of connectives and quantifiers as adjoints is part of this. Actually, it took some time to understand. I think this is just a remark concerning Pino and me, but also many others. So functorial semantics, but this approach allows to identify, for example, generic models, which otherwise, how can you describe? And so, for anyone who was interested in model theory and on semantics, that was a revolution, a conceptual revolution. And the second point was the idea of foundation mathematics, which I think changed the idea itself. I mean, not just a different solution to a problem or a different axiomatization as a presentation of the theory, but a different look at foundation that, as Bill said, is the search for what is universal in mathematics, which is not a completely different idea from what is a set of axioms for zeta f or MPG or whatever else. So I think, but apart from this remark, there would be also a question that I can. But before raising the question, if there's time, I would like to express what I think is a common feeling here. That is that every single person, or most of those who are here, every received from real field, not just an input to understand something that otherwise they would never understand, but a support in understanding further, and in particular in focusing on what was their specific research on the specific problem. This is something not so common, at least I think in our experience, and particularly it's very rare to find someone who, when you give him or her the paper and read it to be published, does not just say this is wrong, this is right, but if there is something which is to be corrected, suggestive, and is the line to correct it. So this is something which is not only rare, but is to be highly appreciated by everyone who devotes his life to research. Well, the question, to put it shortly, you mentioned this between the subcategory of figures, which category provide a set of generators for this is saying that the specific category of figures is the same as, if I remember well, the Isbell's term adequacy for the subcategory, right? So there is a dual notional adequacy, which is co-adequacy, related to the subcategory of, you mentioned it in terms of functional algebra with quantities. So in a context of topos, general, I mean, when you study spatial objects, what the opens mean for a sheet, a category of sheets from a topological space can be recovered in terms of sheets over a site. And there is, I mean, this sort of there is a relationship between the generators, family opens the base space, and the truth value objects. Now, if you consider this, I mean, the question is, consider the subcategory of figures which is adequate in the sense we just said.
Figure shapes. I call it figure shapes.
Shapes.
Figures
right.
are the actual
shape.
general space.
Can we have a sufficient condition in order to identify the quantities which are co-adequate for the category?
No. Well, yes. The interest would be usually in having a small adequate subcategory or a small co-adequate subcategory. But the latter question is already, even to the abstract sense, connected with the matter of smallness. If you look at the category small abstract sense, there should be a small co-adequate subcategory, which Isbell calculated in a very important paper around 1960. It suffices to take all countable sets, not just the truth value of 2, not even just the finite powers of 2 or something, as you might think, no, all countable sets. Or a more geometrical version of the same thing. For continuous spaces, you look at continuous real value functions. So instead of truth, there's real quantities. And you hope to find, now in that case, yes, if you just look at, or even complex numbers, so continuous functions with values in some quite recognizable. So even for the continuous spaces, not just the abstract sense, you should have coexistence. Well, first thing to notice is that this should have is true if and only if there are no rule numbers. So in other words, I am deducing from that, you see, there's a rational definition of small. Small does not mean a member of a class. that has led to a lot of misidentification, which was a good idea when Bernays thought of it, because it certainly not. Oh, and by the way, it was pointed out that she looked in the correspondence of Gödel, collected that. Pfefferman has misinterpreted this, but he has noted that there's a correspondence between Gödel and Bernays in February 1963, which has to be the month when I wrote my thesis. And they were discussing what, according to Dana Scott, they must have learned from Kreisel. It doesn't say where they learned it, since Kreisel was some lab around. He told them that there was some student who was working on the crazy idea of set theory and category theory. And they discussed this. Another input, which was McLean's talk in Warsaw about infinitistic methods, so they knew about that. So they were talking, oh, what is this? What is this category thing? This is very interesting. Oh, immediately they said, their first reaction was, we're going to have to look at v to the power of v and so on. Right? We're going to have types over v. So what? For 50 years or more, category theorists have always been worried about legitimate. Let's be legitimate. Oh, that's illegitimate. So, legitimate with respect to a certain law. The law was laid down precisely by those guys. And their first reaction was, oh, of course we have to modify that law. They have no doubt that it's going to be consistent. I mean, it was because of my set theoretic training, I was not quite sure it would be consistent. I guess set theorists nowadays understand a little better that it's clear that such a thing would be consistent. Equiconsistent. It's not equiconsistent, but it's not a further. No, it is even equiconsistent. So you could just adjoin this without creating any new problems. It's just for the convenience of being able to drop this bullshit about the legitimacy. It's not. But of course, then it's not. But you see, so in other words, I think it's crucial for mathematics. Mathematics takes place in the category of categories because structures are functors, everything is really functors, and that's the simplest way to think of it, as you pointed out. But then one of the axioms about the category of categories is that there exists an object called the category of small sets. It has to be an object, not just a class, not just a subcategory of the universe. It's an object. And of course, it's Cartesian closed. It's a topos, and it's fully embedded in the universe. That's the hard part. And it's fully embedded. If it weren't fully embedded, it's just the consistency. The near consistent. This is some sort of super consistency. But the other thing, precisely because of this desire for a small coed, which Isbell showed that it's not only rings of continuous functions, it's in bornological theory, the whole series of theories of analysis and topology, that you get, roughly speaking, a nice duality between space and quantity, which is this idea of coadequacy. If and only if there are no, so one of the things that must be true about the category of small sets, that even though, independently of whether you have measured the coordinates outside, somewhere in the same category. In it, there are no. I mean, the whole category is Cartesian closed. It's essential. So you can form S, if S is the category of sets, you can form S to the power S et cetera. All these things are legitimate. But the point is that in S, of course, those things are not any more locally finite any more than the category of finite sets is itself finite. But you have to exclude. Now, to exclude it is just the equation that says we have coadequacy. It's just a statement that a certain naturally defined comonad is distributed identity.